started. Are you ready? Chapter 2. Here we go. Great. You ready? What are we going to do? You're going to hate this section. You're going to hate this chapter, possibly hate it, because it's graphic. The whole point of this is so you can see how these linear programming problems are solved, so you realize what the computer's doing when they solve it. And in the old days, we had to do this to actually solve it, because the computers didn't exist yet. That's how old they were. Right? There was no such thing as a personal computer, and especially not a phone that's a computer. My first car phone was this giant thing in the car with a little huge thing going in my truck where there's a big box that's controlling it. And now it's in my pocket. Almost too big. You get it? Here we go. Blah, 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 blah. Graphical solution method. Wait. Let's do this. Some of you need review. Right? This is all heading to where you got to take these equations and you got to apply either the subtraction method, the addition method, or the substitution method. And a lot of you have not seen those methods in a long time, so I want to make sure and demo them for you. I'm only going to demo one, and the rest I posted today on Blackboard. So if you got the materials early, you may not have gotten this one. But I went ahead and did it, typed it all out, what I'm about to show you, for all 3 examples, so you can have it while you're taking the quiz. What I want you to do is you only have to use one of these. If it's the subtraction method that you go, oh, that seems easy, then you should use that one when we get to that point. If it's the addition method or the substitution method, whichever one reaches out to you and says, oh, that seems easy to me, that's the method you should use. So I'm just showing you 3 different methods. This is going to be 0.7 s plus d less than equal 630. This equation is going to be s plus 2/3, I'm just abbreviating, 66666, d less than equal to 708. You're told, hey, these 2 equations, I need to know, using one of the mathematical methods, where they would cross on a graph. And here's how you do it. You look at these 2 equations and you say, now I'm going to do the subtraction method. So this is going to be subtraction. And you look at this and you say, how can I convert one of these equations so that when I subtract it from the other equation, it cancels out a variable? Like if this were 0.7s, I could just subtract these and s's are gone and I could solve for d. Or if this one were 2/3 d, 0.6667, I could subtract them, d would be gone, I could solve for s. So I then look at this and say, the easiest way for me to convert one of these so I can subtract them and get rid of the variable would just be multiplying one of the equations by whatever it is I want to turn it into so I can subtract it. So I want to subtract this. This is 1s, this is 0.7s. I need to make that 0.7s. But if I multiply this by 0.7 to change it, anything you do to part of an equation, you have to do to the whole equation, the whole thing. So all the way across, I got to multiply 0.7 times all of this. Here's the calculators. So someone help me with this on a calculator so I don't have to? You ready? Obviously, 0.7 times s is 0.7s. But what is 0.7 times point? Give me at least 5 sixes. 6, 6, 6, 6, 6, and then put a 7. Or more, any more sixes you're willing to put. Times 0.7. What do you get?
0.46.
0.466666?
Yeah.
Oh, whoops.
Wait, aren't you multiplying a -7?
No.
Okay.
If I were going to add them, she's jumped to the addition method, which you would exactly do that.
Okay.
But I'm going to use the subtraction method, so I want to leave it positive. I'm just straightening this off. You said 0.466666D, right?
Yeah.
Okay, now what's 708? And watch, I'm changing this to an equal, just so I don't get confused. I'm changing this one to an equal also. 708 times 0.7, is that 400?
495.6.
495.66666?
No, just 6.
Oh. Okay, now this equation is gone, and we got this equation. Now I'm going to use the subtraction method, and I'm going to be able to eliminate one of these. By the way, this new equation is the exact same as that equation. They would overlap each other. All we because as long as you're changing each part of it exactly the same as all the other parts of it, it's the same equation. I'm now going to subtract 0.7s minus 0.7s, gone. 1 minus 0.466666 is 0.54444?
Yeah.
Or is it 3? Is it 3?
0.53
3 repeating, yeah. There we go, D. And then now I have 630 minus 495.6. That's going to be 135.6. 134.4. Thank you. So now I only have one variable. I was able to get rid of a variable. I divide both sides by 0.533333. And I get D equals 134.4 divided by 0.5553 is 400? 600. 690. Damn. What is it? What is 134.4 divided by 0.533333? Yeah, I got calculators going all around. No answer.
252. Even.
Everyone agree? 252. Got confirmation. We just found that these two equations will have the point at which they cross. The d-axis is at 252. Now the d's this way. The s, we plug in 252 for d in either one of the original equations, and we'll know what s is. Pick either one, doesn't matter. I'm going to pick the top one. So now bring that down. 0.7s plus, I'm now plugging in for d, 252, equals 630. I changed that to equal just so I don't get confused. Subtract 252 on both sides, I get 0.7s, that's an s, equals, what's 650 minus, or 630 minus 250 is 380?
378.
That's what I meant. 378. Now divide both sides by 0.7, and s equals 600. Damn.
540.
540, there we said 2? 540. 540. You ready? If I were to graph this, I would go to D. Here's my axis. Hey, I can't remember which one's S and D. I think S is the horizontal.
S is fine.
There we go. Here's my S axis. Here's my D axis. And those two constraints are crossing at 242, 540. 242 about right there, 540 about right there, approximately. So if we had lines on that graph, we would see them crossing at that point these two lines. What you just learned, yeah, and if you take the time, here's the subtraction method. What did I do here? Multiply this equation by 0.7. All right? In order to have both constraints with at least one variable the same. So when you subtract, it will eliminate it. The result, 0.7s plus 0.4666 d. Is that 9? 4669? Is that true? Is this not 0.46666? Is that what I have at 9? Equals 495.6. Is that supposed to be a 7 there? Anybody?
That is supposed to be a 7.
Is this supposed to be 7? Everyone agree? No one cares. Now subtract the results from each other. Take this equation minus this equation. These two cancel each out. You have this minus this. Left you with 0.533331 because I used a 9 for some reason. D equals 134.4. We divided both sides by 0.53. We got 252. I had to round it because I had the wrong number of it. I probably should switch that to a 7. I went on, plugged 252 in this, and got 540, just like you did, yes?
Hold on, one more time. How did you get the 0.5333?
I took right here,
Okay.
0.7s minus 0.7s eliminates s.
Yeah.
1d, there's no 1 there, but that's 1d, minus 0.444666, that should be a 7. That's how I got to 0.533d. Let's switch that right now, because this is posted. I have to repost it tonight with the correction. You think I'll remember? Yeah, I don't either. I'm actually hesitant doesn't change. I rounded, so I can get the word rounded off. It's probably exact now. 2 this turns out to be 540 after you plug it in. Scroll down. Here is the substitution method. What do I do? Oh yeah, I'm going to jump to the addition method. The addition method is exactly the subtraction method, all right? But instead of multiplying by positive 0.7, you're going to multiply by negative 0.7, which turns out to be negative 0.7s minus 0.4666d equals negative 495.6. And then when you add them, you're adding 0.7s to a negative 0.7s, which eliminates it. And then you have 1 plus a negative 4666, you get the same answer, 0.53. Then you have 630 plus a negative 495, because it's the addition method. You get the same answer. Divide both sides, you get the exact same, everything's the same now from this point down. So that's the only difference between addition method and subtraction method. Substitution method. This is where you're going to take one of these equations and you're going to move everything to one side except for one variable all by itself. So either you're going to make this s equals something or d equals something. So I said I'm going to subtract 0.7s on both sides because that will leave d all by itself. And I get d equals 630 minus 0.7s. Now that d is all by itself, I take the result, plug it in for d into the other equation. So now the other equation, we substitute it in the other equation for the variable d. So now the other equation is s plus 2/3 or 0.667 of d. But instead of putting d there, I'm inserting 630 minus 0.7s equals 708. Then I have nothing but s's there. D's gone. And I can solve for s, and I can multiply both sides by 0.667, or what's in the parentheses, and I get this equation. And then the constraint is now s plus 420.21 equals 0.46669s equals 708. This goes on right here. Where am I? I can't tell what that is. Is that plus or minus?
It's a minus.
Minus, thank you. Then subtract like terms. Combine your s's. Move the 420 over. 0.5331 equals a different number. What happened here? Oh, because I'm doing s and not d, excuse me. Then divide both sides by 0.5331. You get s equals 540. Plug in 540 now in either one of the original equations, doesn't matter which one, original ones, and it will show you d, which is 252. The same answer, whether you use subtraction method, addition method, or substitution method, they all get you the same s and d, just different ways of getting there. And you can print this out and have it right next to you for the next quiz.
Will we have to know all of them, or will we be able to choose?
You choose whichever one reaches out to you and you find the easiest. That's all you need to do is be able to master one of these. Because on your quiz, you're going to have a question, and it's going to say, you know, it'll be a graph probably, it will say find the optimal solution. And you're about to learn how to find it. Then it will say solve for the optimal solution. You then got to say, well, here's the optimal solution, this point right here. But what constraints are crossing at that point? And you identify what the constraints are. You go, oh, this constraint and that constraint. And then you got to use one of those methods on your quiz to tell me, to show me you can come up with what d or s or whatever the variables are, what they equal using one of these methods. Subtraction, addition, and here they are. It's my first time typing it up. Just do it. I was just too lazy to type. I don't know. I'm sorry?
Appreciated.
What?
Appreciated.
Oh, yeah. So now we've reviewed our math. We're ready to do a problem. You're going to see step by step how to solve it and find the solution. You ready? Here's the steps to formulate a linear programming problem, just like the tortillas, the sugar suppliers. You know, understand the problem thoroughly, describe what the objective is, describe what each constraint, what the limitations are. Define your decision variables. From now on, you're reading it saying what decisions need to be made, and you define them. You put a variable, what they equal, how many or how much of something. Then you write your objective function using those variables, and you write your constraints using the decision variables. This is how you do linear programming. Then you're going to solve it. For this next quiz, you're going to solve it via graphing method. But from that point on, you're analyzing the outputs from computer outputs or Excel. So this is a one-time that we're going back into the past, and we're seeing how this is done manually and how to come up with the answer. There's a company called PAR. They make golf equipment. They said, we want to start golf bags. They talked to some of their distributors. One distributor said, we love this idea. We love your other equipment. However many golf bags you can make in the next 3 months, we'll take every one of them. So they got a purchase order saying, however many. You guys know what it means to be a company that has a purchase order that's as good as cash. Consider that cash. Purchase order is a promise from, you have a promise from a buyer, and when you have that purchase order number, that means go to work, start making them, because we got the money coming. After you get done making them, you give it to them, most companies will give them 30 days to pay for it. So they have time to start selling the golf bags to generate money to then send to us. You try to encourage them. This is real life. You try to encourage them to pay early. All of our bills we went out, and when I was in the accounts receivable, all the bills that came in, they had what's called a discount period. So when you get an invoice, it says $20,500, 2% 15, net 30. Anybody counting? Ever heard that before? Come on. Yeah, what does it mean? What is the 2% 15, net 30? You got the invoices, $20,500. What does that mean?
I haven't seen it in a while.
What does it
You
mean?
get like a certain discount if you do it before the 30 days is up.
No, before the 2% 15 means you can take a 2% discount if you pay us in 15 days from the invoice date. That is a big deal. To get 2% off for 15 days, I could, I always made sure we paid our bills within that period to get the discount. I could never make the money by investing it in anything as much as 2% in 15 days. There's nothing I can make 2% on in 15 days. It's like making 2% on your money for 15 days by taking advantage of the discount. And then some people take the whole 30 days. What happens with a lot of manufacturers, when they get all these purchase orders and they're making a bunch of stuff, they don't get their money sometimes until 30 days. And if sales go slow, they won't pay sometimes for 60 days. That straps you as a manufacturer, because if you're not getting your money in a while, where are you getting the money then for the raw materials to keep production going? So that's a lot of problems that a lot of manufacturers have. The next student has a manufacturing company over in Grand Rapids who contacted me last semester and had this exact problem and was not offering discounts on their invoices. So that was the solution I came up with. I haven't heard back if it's working or not, but they said they were not doing that and they need to get money faster. So they're offering discounts now. And I would assume that whoever's buying their stuff that they're making is hopefully taking advantage of discounts to keep their money faster. Here it goes. So this company says, we're going to do 2 golf bags. We're going to do, we got a medium and a high price golf bag. So a standard and a deluxe type of thing. Here are the departments that they've analyzed exactly what has to go through, and they've made some demo bags to see what the process is, the quality, what's involved. Accounting was given all the numbers from the suppliers of every piece of material that goes in the golf bag, including the cost of labor and the overhead. So they can evaluate if this is going to be a profitable venture and how many orders would have to be to make sure they want to invest the money to start a new venture like this. If you're doing a new product in manufacturing, this is a big deal because there's a lot of money up front that you're going to put up to do this product. So, in most cases, companies I've analyzed, when they're going to start a new product, they're looking at a minimum of $1 million to start a new product. So you're doing a lot of testing to try to make sure, is this the right decision? Because if this product if we see something and it doesn't happen, and it doesn't sell, we could lose $1 million. So that's why it's such a big decision. Here's the 4 departments it has to go through. Now, this is all about each of these departments only have a limited amount of hours in this first production run when they're for this first supplier. So this is all about the first 3 months. How many can we make of each of these bags with these limitations? Because we've already got these departments making other things. So each department had said, we have this many hours for the next 3 months, this many hours, and this many hours. So we had to evaluate how much time each one of these 2 golf bags are going to take in each department. here's the hours, or here's the amount of time. If all the standard bags we're making, it's going to take 7/10 of an hour in this department, a half an hour here, an hour here, and only 1/10 of an hour in this last department. The deluxe bags, a little more time in the first cutting and dyeing, a little more, a lot more time in sewing, a little less time in finishing, and a little more time in inspection and production. There's more money involved in the deluxe. Now, marketing measures, 1. That's it. No one else is marketing. 2, 3. You're going to learn all about the good, better, best system of marketing. Does anybody have that yet in your classes at all? Good, better, best? Anybody know what I'm talking about? Oh? Huh? Many, many companies, and I used to work for a manufacturer. One of my first jobs out of college, I was teaching industries. We made bathroom stuff. Everything you can think of in the bathroom. And a whole marketing concept, they had it all designed before I ever got there, was the good, better, best system, which many companies do. You're all going to learn about it in the real world after graduation very quickly, especially if you're working for a manufacturer. Good, better, best says, we're going to make this product, and this is going to be our price competition against everybody. But then we're going to make a little better one, hoping the customer will say, I want a little better one. And almost every company doesn't have that much more process involved in making a little better one. So the profit is usually bigger on the better one, but then the best one. We call this the Rolls Royce of toilets. The low profile, elongated seat, one piece. There's a little bit more time involved in the manufacturing process, but the price is significantly higher. And so almost every company has that good, better, best because they hope a customer goes to the best because there's some options they love about it, or the better. There's always more profit in the better and the best than there are in the standard one. The good one, you're competing against. Back in my day, there were so many coming up from Mexico that we had to keep lowering our price on the initial one to compete, and to the point to where we were selling to our distributors at a loss just to keep their business, making it back up when they sell the good and the best, the better and the best one. We make so much money off those two that it was okay to sell the standard one at a loss. Doesn't that sound crazy? That was our philosophy in order to keep the business, because the competition was coming up from Mexico was so rough. So there you go. Can you see where this is going though? Literally the constraints are kind of written for you right here in this table. The only thing that's missing is, what is this variable? What is that variable? And these are all going to be probably less than equal to some limitations on how much time is available. All right, what's the decisions that have to be made from what you've been told so far? What decision has to be made? Anybody? Name it. How many? What? The bags, standard bags. What about the bags? We're a manufacturing company. We're about to go to production. We got these 2 bags, but there's a decision to be made that you're hearing about right now. And I'm hoping it jumps out at you a little bit. How many decisions do you think there are that this is all about? How much or how many to make of each bag. We don't know how many standard we're going to do. We change it up and start making the deluxe. We don't know how many. Because, here's some additional information. There's a limited number of hours in each department. We knew that was coming. The director of manufacturing says 630 hours of cutting and dyeing over this period of manufacturing we're scheduling. 600 hours of sewing, 608 hours of finishing, 135 hours of inspection and packaging. That's all that's available because we have other things going on in these departments for this additional thing going on for that 3-month period that we're trying to schedule for this distributor who said as many as you can make during that time, we'll take them all. Here's a blank purchase order, which means they promise to pay for them. That's what a PO stands for. The accounting department analyzed the production and arrived the prices of both bags and the result profit contribution, $10 for every standard bag, $9 for every deluxe. In real life, that'd be more like 14. Almost every company I've ever analyzed or worked at, the deluxe bag would be a bigger profit than the standard bag. The standard bag is built to face the competition, to be in there at the price point. The customer comes in, you train whoever's selling your stuff. We used to go to Handy Andy's and Home Depots and I can't think of the other ones, Forest, whatever they were back then. 84 Lumbers, do they exist anymore? 84 Carter Lumbers? Anybody know what I'm talking about? Home Depot, how about that one?
Yeah.
Lowe's had not existed yet. And we would literally make appointments, drive out, go to these stores and train, because we went directly from the manufacturer to the retailer. And we would go to the retailer and train their staff to try to help them to upsell the customer from that standard one, show them the features of this good one. Maybe they would want that. Show them the features. Here's what makes this one so much better, the best one. And you point it all out so that they can repeat it then to the customers that they're meeting with who are thinking about buying these bath fixtures. That's what companies do. They go and train whoever's selling their products to try to, so they can make more money. So in real life, this would be a higher profit, and this is why we go out to show them how to upsell. It's called upselling, marketing majors, upselling. So, max or min? Max, because we've just been told profit, so odds are we're trying to decide how many to make based on these limitations of how many hours we have in each department, and we're probably going to want to maximize profit. You want to make more standard bags or deluxe bags, probably? Yeah, you make more profit off standard, right? So, here's the constraint and the objective function based on that information we just heard. The objective function, max, first we identify the variables. You told me there's two variables. We're going to use S and D. S is how many standard bags we're going to make. D is how many deluxe bags we're going to make and send off to this distributor who's ready to pay for them. $10, $9, never putting equal. Never put a less than equal. Never put a greater than equal. There's two of you in here. Don't do it. What'd you lose? An eighth of a point? It will be more. Because this is like a pet peeve. This is not a constraint. Every single constraint has to have a less than equal, greater than equal, or equal. Yes. But never the objective function. Here is, hey, it takes 7/10 of an hour, and at 1 full hour in this department, 7/10 times standard bags, 1 times deluxe bags, less than equals 630. It takes a half hour and 5/6 of an hour in the sewing department, so a half an hour for every standard bag, 5/6 of an hour for every deluxe bag, less than equals 600, and so on. Does everybody see how these are made? When you get these problems on a quiz, stare at this part of the problem because it's almost telling you what the constraints should be almost. I mean, there's a lot of these you're going to see. It's almost telling you, it's set up to show you, like this one's set up to show you exactly this constraint that has to do with cutting and dyeing. I mean, you just put the variable there, put a plus, less than equal. Put a variable there, put a variable there, put a plus, less than equal. They're almost set up for you. Okay? Here they are. There's 4 constraints. Again, in this all semester, the variables are always positive. You don't have to ever put this greater than equal to 0. You can leave it right off for the whole semester. They're always positive. And now, are you ready? Now you graph each constraint. You are so lucky because this morning, whoops, where'd it go? Whoops, turn that off. Again, here we go. This morning, I went ahead and penned this out. I practiced it and I thought, why shouldn't I just save it? I can't get this pen to write because I'm left-handed, my hand hits, and the whole thing moves. So it's very difficult. Even if I don't tablet, still my hand hits. So here it is. Here's the constraint, the first one we're going to graph. You put a 0 in for one variable, solve for the other. You put a 0 in there for the other variable, solve for the other. Let me say that again. I got set up to where S and D, S and D. We're going to put a 0 in for S and figure out what D is. Then we're going to go back and do it again by putting a 0 in for D to figure out what S is. Here's the constraint. There's S right there. So 7/10 S plus 1D, I'm going to make it equal to 630 right now. I'm making it equal so I don't get confused. I'm putting a 0 in for S. 7/10 times 0, S is gone. What's left? 7/10 times 0 leaves you with D equals 630. So, again, right here, for D equals 630, I placed it there. I'm putting a dot at 0 say this is 400, 600, 800. Is it S or D equals 630? D. Here's 600, and here's 800. So I'm going to put a dot right here at 630. 0S, 630D. Now I'm putting a 0 in for D. Go right here, right here. 0 in for D. So now I got 7/10 S plus 0 equals 630. I'm going to turn 7/10 into a decimal. See, it's easier for me. So 0.7S equals 630. Divide both sides by 0.7. S equals 900. I placed it here. The point that this equation crosses the S-axis, is at 900. The point that this equation crosses the D-axis is 630. What was this one, 900? So I'm going right here, you put 1,000 here. Here is 900, right there. Now I'm going to take a straight edge, connect the dots, because all of our equations, you may get dots down here, and you may get dots over here, but when you connect the dots, bring your lines into this quadrant, because our answers are all right here in this quadrant. It will never be in this one, or this one. It's all right here, because our variables are always positive. So I'm going to connect these two dots. Let me get rid of that one. Hang on a minute. I don't have a straight edge. Okay. Close. There's that one. Now you go back and look at the original equation, and you say, if you pick any point, either this side or this side, you plug it in, and you say, does it make sense? Is it less than or greater than whatever the equation says? And if it is, that's the direction you're going to shade. If it's not, you're shading the opposite direction. I love picking the lowest point right down here, like 200, 200. This is my favorite. So 200, 200, I'm going to plug it in for S and D in the equation. And if it's, let me see what the equation says. If it's less than or equal to 630, I know that this is the way I should shade. If it's not less than or equal to 630, then I know I should be shading that direction. So I'm going to plug in 200, 200. Is this one right here? What a coincidence. 0.7 times 200 plus D is 200 less than equal to 630. 0.7 times 200, that's 140 plus 200 equals 200 equals 340. Is 340 less than equal to 630? Yes or no? It is. So that means, now I don't want to shade the whole thing, we're just kind of lightly, because this is, we're heading to where you've got to erase some of the shade, kind of. So I just put it in lightly, and now I know that's the direction of that constraint. So we now graph that constraint. And you do this with each constraint. You put a 0 in for one, you put a 0 in for the other, and you find the 2 points and you connect them. So,
Where'd you get 200?
I went ahead and picked any point at random. And I picked on one side of the line or the other. Okay, one side or the other. And so I like using like this down here. It just makes it easier for me. But you could have went with 800, 800. Is that up here? Or what about 600, 600 is up here? Any point you want. If I would have went with 600, 600, look what happens though. 0.7 times 600 is 420. And then 600 for D would be plus 600. These equal 1,020. It's not less than equal to 630. So I know now not to shade that way, and I don't need to recalculate. I know that shading goes the other way. The hint was also, this is a less than equal, so it kind of makes sense that you'd shade towards the numbers that would be smaller, that would get the smaller result. All right, look at this next one now. You ready? Okay, here's this again. This is the one we did. 900, 630, connect the dots. This one, this is a purely a coincidence. This is a new PowerPoint. I did not even know 200, 200 was the point to be tested. It's just a coincidence. Testing 200, 200 to figure out which way to shade. You'll see that shading goes this way. How's everybody? Is everybody feel comfortable with this? I mean, because the other constraints, the other two constraints. Here's the shading on where's the 900 again? Well, there's 3 more constraints. So these are the other 3. We plug a 0 in for S. We would have got 720 on this one. plug a 0 in for D, we would have got, does that say 1200? Close. Okay, on this one, this constraint is half S plus 3/4 D or something like that equals less than equal to 600. We pick any point on either side, we plug it in, we know the shading goes this way now, less than equal to 600. This one, put a 0 in for S, we got, it looks like 1162 maybe. Put a 0 in for D, or D, we got 768 maybe. Connect the two dots, here's the equation, pick any spot, 200, 200 again, plug it in, it's less than, that's the shading. Same with the fourth constraint. Here's the two dots, we connect them, pick a spot on either side, figure out which way to shade. For this second quiz, you have to show me you can graph these by putting zeros in for one of the variables. You're going to show me that you're testing a random point to show me you can figure out which way to shade. At least one constraint, I need to see that work, that you can do each of these steps. Then, after that, you have all of these on top of each other, not separate like this. You're not doing separate graphs. These are all on one graph. And then you look at this graph and you say, where are all 4 of these shades overlapping? Not where 3 of them overlap and the other one's not, or 2 of them. Where are all 4? It has to be every constraint overlapping. And what you identify is what's called the feasible region. This is where every single constraint's shading overlapped. On the quiz, you're going to put an arrow and identify and put nice dark lines along the edges here and say feasible region. Showing me that you can see that's where all the shades overlap. And someone's going to include, see that little triangle there? 3 of the shades would have been there, but not the 4th one. It has to be all constraints shades overlap, all of them. No matter if there's 2, 4, 5, 6 constraints, it's where all the shades overlap. Our optimal solution is somewhere in this region right here. Any of these numbers right here, 200, 200, 400, 400, 400, 200, how's that? All of these are possible solutions that meet all the limitations on those constraints. See, people packing up. We get to that? We're okay? Getting over well? Are we ready to still go? Go ahead.
Where did the 900 come from?
Okay. You ready? You're talking about that right there. What we did is we took the constraint, and is that 900 a D? Is that what that is?
Yeah.
No, it's not. Is it? Where is it?
No, that's
That's the S. So you take the constraint, you put a 0 in for one of these, now it's gone. 0.7S equals 630. 0.7S equals 630. To get that S all by itself, you have to divide both sides by 0.7. S equals 900. If you take 630 divided by 0.7, you get 900. Now we know that D was a 0, S was 900, so the point at 900 zeros is right there. And then you get the point here at 0, 630, connect them, shade. And each constraint's that way. Like if you said, how did you get, is that 768 or too close? Does that say 768? We ended up putting a 0 in for D on this equation right there and solved for S, and we got 768 or whatever that says. And then we put a 0 in for that one and solved for that one. So it's all about putting this, you take an equation, you put a 0 in for one variable, solve for the other, put a 0 in then for the other variable, solve for the other. And those are your 2 points, you connect and you figure out the shading. But here's something I want you to recognize. How many places are there lines crossing, forming a point, and touching the feasible region? Now let me repeat that, because I don't want you to get confused. How many points do you see that are touching the feasible region, and there are 2 lines crossing? And I don't mean 2 constraints. I mean 2 constraints, or a constraint with an axis, or 2 axes. How many points? Let me count before you tell me. Okay. How many did you get? I hear 2. I hear 3. I hear 5. I hear a second 5. I hear a lot of nothing. 5 again. You ready? There's 2 lines crossing right here. There's 2 lines crossing right there, which is your 2. But we have a line crossing an axis here, there's a third one. We get a line crossing the axis here, that's a fourth one, and they're touching the feasible region. And then we have this right here, 0, 0, touching the feasible region. 5, these are called your extreme points. Let me repeat that because you need to know what the word extreme points means. Extreme points are the points where two lines are crossing, touching the feasible region. So we have 5 extreme points. Now, there are 2 methods you can use to find the optimal solution because your optimal solution is one of those extreme points. Let me repeat that. You did all your shading, found your feasible region. You identified how their extreme points here because they're touching the feasible region. And one of those extreme points is your optimal solution. At least one. There could be an alternate optimal solution, but odds are there's only one. Go ahead, I'm ready.
Can you point it out again?
You ready? You know what's weird is this one constraint is a different color right here. It's showing you the border of the feasible region. Here's a constraint right here, but here's one where this constraint line is crossing the axis and is touching the feasible region. These 2 are easy. It's 2 constraints crossing here, touching the feasible region. But here, this constraint's crossing the axis, and then you'll have 0, 0 here. Now, I want to show you something real quick. If this feasible region were out here, that would not be a point touching it, obviously. You'll have less extreme points, okay? It's just when it's right down here that you have that extra one there. 5 extreme points, and one of those 5 are your optimal solution. My question for you is, was this a max or a min? Anybody remember? Was this a max or a min? What was it we were trying to max what though? Profit. There's no way this extreme point could be the answer. And in the old days, we would put in 1, 2, 3, 4, 5. 1, 2, 3, 4. We would enter all 4 extreme points in the objective function. Whichever one gave you the biggest objective function, which is maximizing, that's your optimal solution. But there is no way that you can count on any graph to know what these 2 points are. No way. Whatever you think they are, that's not good enough. You've got to know exactly what the coordinates are there. That could be 556.29333. And the only way to find what these numbers are is you're going to say what 2 constraints are crossing at that spot. And you're either going to use the addition method, the subtraction method, or the substitution method to give me the exact coordinates of that spot or that spot. One of them you have in your future. Especially if one of these 2 happen to be the optimal solution. So that's what we're going to pick up on Thursday, is how you figure out which one of these extreme points are the optimal solution. That's it. We'll see you.